All right, now let's get into vector data. Remember that vector data is points, lines, and polygons. These objects have dimensionality. Points are 0 dimensions, lines are 1 dimension, and polygons are 2 dimensions. When we think about these dimensions, they build on each other. Points are 0 dimensions, and you might remember that from high school geometry. Lines are 1 dimension, which connect 2 or more points. And finally, polygons are created by lines which connect points, which then close to create a filled area. 3. The big thing about vector data, beyond knowing that it's made of points, lines, and polygons, is that it has attributes. Each feature, aka each point, line, or polygon, is described in a table. There's a row for each object/feature, and a column for each descriptor of those features. So here are all the counties in Oregon. They're all polygons within a data set. Each of these county polygons then has a line in the attribute table. And each column describes different aspects of each of those records. So here we have things like name, county code, shortened name, the date the county was established. Because GIS is a database, each row is called a record, and each column is called a field in the attribute table. Here are some more examples of attribute tables. One is of polygons on the left. Here we're talking about parcels. So each one has a zone, address, zip code, etc. On the right is a point data set of populated places, aka cities. 4, features can be generalized in a systematic way. We talked about generalization earlier when talking about scale, but here's more detail on how we can systematically generalize vector data by, say, taking out points in our lines or polygons systematically. In these graphics, we've removed those vertices except every few kilometers. Bottom one shows every 25 kilometers that we have a vertice. The next one up, vertices are every 50 kilometers. And the last one has vertices every 100 kilometers, which really generalizes that coastline. Finally, just like all data, vector data is good for some types of phenomena, but not others. Points, lines, and polygons are great for discrete objects that are more abruptly changing, but not for continuous, smoothly changing phenomena like elevation or precipitation. There are several benefits of vector data. First, features have attributes. This is really cool and is the primary element that makes GIS really cool and different than just, say, a graphics software like Adobe Illustrator. We can represent our data using these attributes, find out spatial patterns, and query these tables. We'll talk about that later. These attribute tables work well with a database, which I'll talk about more when we talk about querying our data. We can easily show discrete objects. Points can represent cities, lines can represent rivers. These things are discrete in nature, and they are well represented by vector data. Next, we can delete, create, and modify with ease. Editing is easy to do. We can add and remove features from a data set, and we can even modify these to change where the vertices in the lines or polygons are to change their shape. Next, we have good precision with these types of data because we can decide how precise they are. We can have lots of vertices in our lines or polygons, for instance. This differs immensely from raster data where you have to choose your grid size and you can only describe objects larger than the size of your cells. Finally, vector data works really well for creating routes and networks because there's a thing called a topology. In other words, we can store information about how the different geometries interconnect. For instance, with roads, we can store information like where the roads actually connect. So you know that in order to get on the highway, for instance, you need to find an entrance ramp first. Along with the many advantages of vector data, there's also some drawbacks. You aren't guaranteed to describe a surface, for instance. It's very difficult to show how rainfall changes across the state of Oregon with polygons. That's much easier to do with raster. Next, there isn't any uniformity of shape in the way that raster data provides. So when you look at the graphic on the right-hand side of the slide, you can see that customers, streets, and parcels don't all match. Compare this to the cells that will perfectly overlap in the elevation and land usage data sets. That complete overlap is what makes computation really easy in raster data in comparison. Finally, raster data is better at proximity analysis because we can do things like measure how many cells away something is.